simply just say 300 cosine 45 is the component along the B, because the axes aren't perpendicular. So what I would have to do, which we've already done in essence, is draw a line here like this, parallel to the B, draw a line like this, parallel to the U. Therefore, I have my parallelogram, yes? In which case now I can simply go back and do alter interior angles, that's 45, that's 60, which means this angle is phi. Phi is going to be 180 minus the 45 plus 60. Phi is equal to, what did we say, 75. Now I have 1, 2, 3, and one side that tells me I need to do the law of sines. Law of sines kicks in, and I've got sine of 60 over FV, sine 45 over FU, and sine of 70 over 300. Sorry, 75. If I now solve these two together, I'll get the FU. If I happen to solve this and this together, I'll get the FV. FV 268.97, FU 219.66, or 60. So you got to be careful, because if the axes aren't perpendicular, you can't just simply say 300 cosine 45 degrees. The reason for that is very simple. When I have a 90-degree coordinate system like the XY, and I have this force here, 300, say that's 30 degrees, I can say I have a X, that'll be Fx, and I will have an Fy. But notice there is a 90-degree angle in that triangle, whereas the U and V in this axis are not 90 degrees. Yes? You with me? Please notice when I do components, because Fx and Fy are components, notice I'm still obeying the parallelogram rule, which is head to tail. You can never, ever not do that. So you will always obey the parallelogram rule. So today I want to continue with the next lecture, which is, hey, you know what? This parallelogram rule really kind of sucks to do it using triangle construction. It really, really sucks doing triangle construction. You know, head to tail, then law of sines, law of cosines, etc., etc. It sucks after you go beyond 1 or 2, maybe 3 tops. You get a system of forces that's 100. By the way, if I have 100 forces, how many triangles would I have to create? 99 triangles with 99 law of cosine, 99 law of sine. Oh man, I ain't got that time. That's a long-ass process. I don't want to do that. So we, human beings, came up with an easier method, and the easier method is the component method. let's just do components instead of doing head to tail constants. Because with the components, it's just a bunch of scalars. So, big fact. By the way, this is in the next lecture. Big fact. It says a basic equivalence. There's that word, equivalence. A basic equivalence is always valid exists between the sum of concurrent. What's concurrent mean? What does concurrent mean? If you read the first 8 pages of the Procopy book, which I told you to do. Yes. Everything emanating from a single point. So all the forces are going from a single point. Between the sum of the concurrent vectors and the system of component vectors. What's that saying? Hey, listen. If you work with the force itself, or you work with the components of the force, they're equivalent. They're the same. Don't worry about it. If it's easier, go with the component method. Okay? And I just told you about this. You got to distinguish between that coordinate system and that coordinate system. Okay? So what do? And I know you guys have done this in physics, which means I'm not going to spend a whole lot of time, but I want everybody to be on the same footing. I never ever take anything for granted. You're supposed to know math. Did I take it for granted? No. I gave you a math review to do. Okay? When we go to dot products and cross products, which is at the end of chapter 3 for me, I'm going to go through it like you've never seen it before. How many have seen dot products and cross products? Great. How many have not seen dot products and cross products? This is the first time that nobody's raised their hand. So I don't assume anything. I'm going to cover it all. So, what we're saying is we're going to break things down, this force into an x and a y. I'm still obeying head to tail. Please note, fx and fy are scalars. So, I want to say this. F vector, that's why it's bold, is equal to fx plus fy. But I can't. So what I have here is vector equals scalars. Well, I can't make that equal sign. So what do? Ingenious part of us says, I got to make it vectors. Let's multiply fx and fy by a vector. A vector along the x and along the y. That way it gives it direction. And then we said, ooh, we have a slight problem. What's the problem? If I multiply by any vector along the x, I'm going to change that value. Well, that sucks. I don't want to change its value. So what did we say? Hey, let's multiply by a vector that has a magnitude of 1. That's why you multiply by the unit vector. So all we're doing is we're in essence giving the fx a directional sense. The fy a directional sense. And when we do 3D, we're giving it a directional sense in the z direction, which we call the k. Why did we come up with ijk? Who the hell knows? I don't know. We just did. That's what we called it. Okay? So, there's your definitions of ijk. All right. The beauty of this is this forms a right triangle, which means, holy crap, I can use SOHCAHTOA. So, please note, vector has magnitude, has direction, magnitude, direction, and because we place them head to tail, it's obeying the parallelogram rule, right there, head to tail. So I'm good. In which case, I need to know these things right here in order to solve for component method. There we go. So cosine theta is adjacent over hypotenuse, fx over f. Sine of theta is opposite over the hypotenuse. I know you know this, but you know what? I told you, I take nothing for fucking granted. I don't want anybody coming back and, well, I didn't know that. No, I covered it in class. If I covered it, that means it's important. Okay? Tangent theta is Fy over Fx, and of course, from Pythagorean theorem, we know that the magnitude of F is the square root of Fx squared plus Fy squared. Now, if you're sleeping, I need you to be awake. At least give me a minute of your time. Because what I'm about to slap down here is extremely important. You're going to use this fact in chapter 2, chapter 3, chapter 4, chapter 5, etc. Here we go. Big fact. Wake up. How many have had coffee already? How many don't drink coffee? Really? I expected more people drinking coffee. So what do you do to wake your ass up? I don't drink coffee. I did have a cup of coffee this morning, only because I was freaking cold. So I got a 12-ounce just to warm my ass up. But I'm not usually a coffee drinker. What do you guys do without, those of you that don't drink coffee? Coke. Coke!
Coke?
In the morning? I don't think so. Hey, answer that phone. What? Ice? Oh! Poof!
Just get out of bed.
That's a harsh way to wake up. Where's my 5 o'clock guy? There you are. Did you fall asleep early this time? Still 5 o'clock. What time did you get up? What time did you go to sleep? Anyway, so fact, if f is a vector with magnitude of f, then E U lambda. These are 3 ways to say a unit vector, depending on what textbook you use. I believe your textbook Hibbler uses the U. If you read 1950s textbook, it's called lambda. It's the last one there. And a lot of modern textbooks use E. I don't like E because E to me is 2.71, what you know. I don't like E. So I will use probably U, since that's what the book uses. So E, U, lambda, to find a unit vector, what do? You take the vector and divide by its magnitude. Take the vector, divide by its magnitude, you'll get the unit vector. That's great, but more important, I can express any force as a force magnitude times the unit vector. So take this F in the denominator, bring it over to the other side, and you will see this. F is equal to F magnitude times the unit vector. When we get to 3D, that's exactly how we're going to express the force in IJK. Take the magnitude of force, multiply it by the unit vector. Again, what this is doing is giving you magnitude, giving you direction. All right? Huge. Somebody have a hard copy of the textbook? No, not that book. The actual Hibbler textbook. A hard copy. Can I have it for a second? Bring it on to, let's arbitrarily. Chapter 3. Okay, I'm in chapter 4. Let's go to chapter 4. And let's go to 3D. Where the hell is 3D stuff? So look, in 3D, this is an example problem. There's the force magnitude. There's the vector, and what's this? That's the magnitude of it. So the unit vector is, this is the force, and that's the unit vector. There's the vector, and I'm dividing by its magnitude. Which is exactly what I said we would be doing there. There's the force unit vector. There's the force, there's the vector divided by its magnitude. That in the brackets here is the unit vector. Agreed? Let's go to chapter 5. Chapter 5, looking at 3D. Look at it. FAB times what we will see in chapter 2, section 7, RAB divided by its magnitude. Well, that again gives me a unit vector. So you can see 2i minus 6j plus 3k, and I'm going to divide by its magnitude. Square root of minus 2 squared minus 6 squared plus 3 squared. Again, F vector is equal to F magnitude times the unit vector. Okay? That's why I say this is huge. I just showed you two problems, one in chapter 4, one in chapter 5, using exactly this. Okay? You with? Perfect. All right. Let's take a look at a problem. I'm going to do a couple because I know you're pretty proficient in this. That's how you pretty much did most of the problems in Physics 1. How many would say they're good to go with component type? Yes? No? How many are not very good at component type? A few hands. Okay, well, we're going to get good at it. Damn it. Why'd you guys switch? Oh, left-handed. So nice of you to switch with me. You're the man. All right. So it says here, given the force system shown, I got 1, 2, 3, 4, 5. I got 5 forces. How many force triangles would I have to generate? 4. How many law of cosines? 4. How many law of sines? 4, because I need magnitude and direction. And I don't want to do all that work. It's like you're in Calc 1 and you took derivatives. How do you take derivatives the first time? Limit! Oh my God, all that algebra to do the limit. And they said, theta here, xy, and theta there. Here, fx is f cosine theta. Here, fx is what? F sine of theta. So I go back to my question. My true-false question was, fx is always equal to f cosine theta. True or false? Oh, now I have one right answer. Amazing how that happens. Right? I got one right answer. So his response was, well, hey, where's theta in relation? Is it in relation to the x or is it in relation to the y? Because if it's in relation to the x, yes. If it's in relation to the y, it would be this. Again, please note, I would have an fx, fy. Here, I'd have an fy and an fx. Head to tail. To get this, which is parallel to the x, I'd have to say sine of theta, which would be the opposite over the hypotenuse. Agreed? So I'm not trying to hide anything. I'm trying to show you how I take a simple little thing and convert it into a true-false question. So if I gave that today on a quiz, I would say 40% of you would have gotten it wrong. Because I've heard false, true, false, true, false, true. Right? Okay? All right. So, I look at this and it says, I got these 5 forces, I want you to find me the resultant. By the way, everything you're doing in chapter 2, just to kind of get you through this, everything you're doing in chapter 2 is either find a resultant or find a resolution. That's it. Ain't no other type of problem. It's either a resultant or a resolution problem. What is this? Find me the resultant. Okay. This is easy. That's easy because now I have these components here and here. Here I have components here and here. Here I have a component this way and that way. And this one's only in the Y. So I've shown you in red, green, and blue, head to tail, head to tail, head to tail. I'm obeying the parallelogram rule. Agreed? Okay. Now there's one right here. It says 3/4, kind of not visible too well, but it's 3/4. If it's 3/4, what's the hypotenuse? Yeah, 3/4, 5. How many know how to work with 3/4, 5? Okay, let's talk about that before we go any further. So here's the vector. I have that slope of 3. Okay? I can go find the angle. Here's how I would do it. I know this is theta, which means that's theta. Right? So I can come in and I can say, hey, normal, which is fx is equal to, this is f, cosine of 53.13, fy is equal to f sine of 53.13. Agreed? Done. I have the components. Yes? That's one way to do it. Okay? The other way to do it is say, listen, cosine of theta is adjacent over the hypotenuse. The adjacent to this angle of theta here is the 3. The hypotenuse is the 5. So really, technically, cosine theta is 3/5, which is 0.6. Agreed? And I know fx is really f cosine theta. This sucker is 0.6 times f. I now have the x component. I could do the same thing for the y. I could say sine of theta is, and so forth. So I can sit there and say, hey, sine of theta is opposite over the hypotenuse, which is equal to opposite 4/5, which is 0.8. And now I can say Fy is F sine of the angle, but sine of the angle itself is 0.8, so it's just 0.8 F. And never ever really calculating the actual angle. You with me? I don't have to calculate the angle. If I'm given the slopes, I can say the cosine is adjacent over the hypotenuse, which in this case would be 3/5. But I know the component is F cosine there. I just found what cosine actually's value is, 0.6. Same thing here, I actually found the value of sine theta by saying 4/5, it's 0.8. So I don't have to find the angle. Now I don't care how you do it, doesn't matter to me. But I want you to be able to do it both ways. Find the angle and get accustomed to doing it using the 3/5 and 4/5 for the cosine and sine. Because down the road, as you get more mature and as you go through classes, by the time you get to, if you're a civil, by the time you get to structures, which is 2 classes away from there, you should not be calculating the angle anymore. Okay? Everybody understand this? Alright. So, solving this, what I'm going to do is, there's quite a few of them, so I'm going to generate a table. Here's my table. I'm going to write magnitude. I'm going to write x component. I'm going to write y component. And I'm going to make this big because I want to write here something. This will be the 150. This will be the 120. This will be the 300. This will be the 240. And 200. And at the bottom of this, I'm going to sum x's. I'm going to sum the y's. Now the easy ones, of course, are the 150. The 150 is just 0 here because it's only in the y. And on the x, I'm sorry, it's 0 here and 150 in the y. Agreed? Do you agree?
Yes.
What's missing? Yes. And you know why I make that an emphasis here? Is because the number 1 error made on test number 1 is you forget a negative sign. I purposely put in stuff which should have a negative and you forget the negative. Once you forgot that stupid ass negative, you're done. Answer's going to be wrong. Oh, you're on the fail. It's because you make sure that there's a negative in there. No. Here's what I'm trying to do. And this is something all engineers need to be aware of. And you need to become an engineer, which means you need to be aware of. You must pay attention to details. That negative sign is a minute detail that has a profound effect on your answer. So yes, I am going to do shit like this to see if you are paying attention to details. I need to start training you to pay attention to details. Here, it's not that big a deal. In the real world, oh my God. If nothing else, it'll cost your company money. Worst case scenario, you might kill somebody. That's not good. I don't want that on your head. So paying attention to details is extremely important. I'll give you a prime example. Again, from my student who's working on that hospital, sends me this. Sends me this picture. Sends me this picture of a concrete pour. You can see the rebar. What the hell just happened? And the caption in the email was, "Do you believe this?" I said, "Oh." So they poured the concrete. When you pour the concrete, these are the rebars. Why do you put rebar in concrete, by the way? Anybody know? Huh? What's that? Because concrete is terrible intention. It's great at compression, so you put concrete, before you pour concrete, you pour or replace rebar, because the rebar will take care of the tension portion, and the concrete will take care of the compressive loads. That's why you have rebar. Anyway, so they laid the rebar, they poured the concrete, and what happens at the end, they have these tension machines that pull the rebar. And they put a specified tension in the rebar based on what the engineer says. So they poured it, tensioned the rebar, and it exploded. Now, the question becomes, why the hell did it explode? So this is the schematic of that area. This is the elevator shaft. So the rebar had to come around, and it's not straight, it had to come around and curve around the elevator shaft. And it clearly on the diagram says, hey, 36, number 3 hairpins required. That's these guys right here. These stupid looking lines right there. Those are the hairpins that are required. And it doesn't say optional. It says required. What do you think happened? They didn't put the pins in. It's clearly in the diagram. So somebody didn't pay attention to details. Somebody didn't pay attention to details. Luckily, this was during the construction phase, so nobody got hurt. But you just cost your company big bucks. I believe I was told that area needed 14 truckloads of concrete. Plus all the rebar. And the most expensive portion, besides the concrete and rebar, is the actual labor to pour it and get it nice and smooth. So now they have to destroy everything, take everything out, redo it, re-pour. That's dollars. That's money that the company just lost because you laid it, you're taking the hit for the dollars. Okay? So it didn't hurt anybody, but it cost your company money. You're not going to look good in the eyes of your boss. Why didn't you catch that? Oh, fuck, I don't know. I was an idiot. I didn't follow Nora's rules of, hey, pay attention to details. And the reason I was sent that was, you believe this? We didn't pay attention to details. And we got this problem. I said, yeah, I get it. So for you, paying attention to details is, hey, don't forget the damn minus sign. So here, I got to put in a minus sign or else I'm going to be wrong instantly. Instantly. 120. 120, this is going to say 120 cosine 15, 120 sine of 15. That would be 15 sine would be the opposite, so it would be the y. Cosine 15 would be the adjacent, that would be the x. This number is 115.91. This number is 31.06, but I need a negative here because it's pointing downward. Here, these numbers are all positive because it's to the right and upwards. This is going to be 3 over 5 times 300. This is 4 over 5 times 300. So I'm using the slope where I say, hey, 3 over 5 is really cosine of the angle. And 4 over 5 is the sine of the angle. I don't really need to find the angle. See what I'm doing? Which makes this 180 and makes this 240. This 200 is easy because it's a minus 200 and a 0. And the 240, this is going to be 240 sine of 30 and 240 cosine of 30. Sine of 30 gives me the opposite, which is the x. Cosine gives me the adjacent, which is the y. This is going up, so this is a positive 207.84. This is a negative 120. Sine of 30 is a half, half of 240 is 120. Now, sum the column. Summing the column, I'm going to get minus 24.09 and 266.78. So what you're telling me is the resultant force is negative 2409I plus 266.78J. That's what you're telling me. Yes, that's exactly what I'm telling you. Just by looking at that resultant, where does the resultant lie? The first, second, third, or fourth quadrant? Second. How many know that? How many don't know that? Raise your hand if you don't know. Don't be shy. Everybody's good. I don't need to explain it. Negative. Positive. What quadrant is this in? If this is 1, 2, 3, 4. Negative, positive. It's in the second quadrant. Okay? Now I can, if I wanted to, say magnitude of this is the square root of negative 24.09 quantity squared plus 266.78 quantity squared. Square root of that tells me the magnitude is 267.86 pounds. What allows me to say this? Yes, it's a Pythagorean right there, but why can I say this? Because x and y are 90 degrees apart. That's why I can say this. And to give a direction, theta is equal to tangent inverse of 266.78. Divide this by 24.09, giving me 84.8 degrees. And I would say it's in the second quadrant by saying this. This tells me it's in the second quadrant. Now, if you're looking at Hibbeler, Hibbeler might give you, here's the 267.86. He may give you this obtuse angle. Because he likes to measure everything from the positive angle. I do not want the obtuse angle. Just give me the acute angle of 84.4 or 84.8. So I want this angle. I don't care that it's measured relative to the negative x. It's just the horizontal to me. Okay? Any questions on this? Yes.
On the test, you want us to specify which quadrant?
Yes, I want this, and I want this. So when you give me an answer, I need three things. I need its magnitude, I need the angle, and I need you to tell me which quadrant that it lies in 2D. 3D, I'm not worried about. 2D, I want to see this. Okay? Now, it then says in the statement, that's part A. Part B, two forces directed along OA. OA is in the y direction, OB, which is along this dotted line, so that the resultant of the 7 forces is 0. So what I want to do is I want to add to this an FOB and an FOA. And then I'm going to sum the x's here, and I'm going to sum the y's again. FOB, there is no x, because, no, sorry, that's FOA. There is no x. It's only in the y. So this would be just simply FOA. In the y, for FOB, again, I would have an x and a y, which means this would be in the x minus 0.866 FOB and a minus 0.5 FOB. What did I do there? I basically said, hey, for FOB, I want the x component that would be cosine of the angle, 30, which is 0.866, and sine of the angle 30, which is 0.5. Now, sum this. Summing this, I would have minus 24.09 minus 0.866 FOB. Here, I would sum this 266.78 minus 0.5 FOB plus FOA. So my resultant is 0I plus 0J. That's my resultant. It said it was 0. It's got to equal to minus 24.09 minus 0.866 FOA I plus 266.78 minus 0.5 FOB plus FOA J.
Can you lower the?
It said in the statement the resultant is 0. Well, the resultant 0 means 0I, 0J, and if I were 3D, 0K. Yes? That has to equal to the IJK. Are you guys dancing? Oh, you have to keep one. No, thanks. I appreciate it. No. So now I'm going to equate i's. I's on the left is 0. I's on the right is minus 24.09 minus 0.866 FOA. This is going to tell me FOA is equal to FOB. No, it's FOA. Oh, yeah. Sorry. FOB. So FOB is equal to minus 27.82. If I now take this and dump it into here, I can find FOA by saying 0J, this is all the J, 0 is equal to 266.78 minus 0.5 times negative 27.82 plus FOA. FOA is equal to negative 280.69. Done. Can you see that? Kind of. I need to move a few things. There we go. questions on this? This is the component method. I'm sure you're very well versed in the component method. I want to do this problem just to have everybody on the same footing, plus introduce the slope thing, the 3, 4, 5 thing, where I don't have to find the angle because cosine of theta is really adjacent 3/5, which is the hypotenuse. So I don't really need to find the angle if I wish not to. If you want to find the angle, by all means, have at it. I don't care. But I need you to see this and start kind of using it. Because down the road, 2 classes down the road, especially if you're civil, when you take structures, they ain't gonna find the angles no more. They ain't gonna find the angles no more. Okay? By the way, nobody likes teaching statics. You know why? First of all, it's huge. Nobody wants to teach a 270 student class. I don't give a shit. The more the merrier. Second, primarily, I get teachers coming in. You know, my class, blah, 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 whatever it is, it's got 85 students in it. I said, stop. I'll trade you. You take statics, I'll take your class. Oh, no, I don't want that. And why don't they want that? A, it's too big. And second, I don't want to deal with your babies. I don't want to deal with the babies. You are, in essence, a little baby right now. You are not even in the crawling stage yet in terms of your education. And you kind of make here's a baby, here's your education. As an engineer in education, you are in the baby stage. Nobody wants to deal with you. At least not the other teachers. I don't care. Bring them on. Somebody got to train you. I'm okay with it. I'm okay with the big class. I don't care. I got professors, hey, this student needs to get in. Oh, the class is full, it's got 85. Can you take one more? No, not doing it. Are you serious? How many were just added into this class? This week? Were you just added into the class? It's because they called me and said, can you take another one? Yeah, well, what the fuck? 271, 272, what the hell's the difference? Once you're beyond 50, it don't matter. Or 80, it doesn't matter. I like some of them. I'll get about 50. Yes. You know how easy grading that is? And by the way, I grade my own tests. I don't have my TAs graded. Because I want to see for myself what you're doing wrong. And you say, well, why do you want to put yourself through 270 some odd students? No, it's really more than that because I have dynamics class too. Total this semester is 472. That's how many I'm teaching. 472. And by the way, in 2024, fall, spring, summer, I taught 999 students. What do you mean am I okay? What cycle? Teaching 999 students? Without coffee! Listen, I wish you one thing. I don't wish you wealth. I wish you two things. A, health. And B, a job that you love. If you have that, your job's not work. This job, it's not work. I go to have fun. I'm having fun. Can you feel me having fun in this class?
Yeah.
Sometimes.
This is fun. I worked at Lockheed. I was miserable. The The reason I was miserable is they put me in research and development. I have a cube, this big old room, all bunch of cubes. You have your own little cubic desk, and that's it. And you just crunch things out. And by the way, I'm going to tell you how I became a teacher. I did not plan on being a teacher. Here's what happened. Lockheed laid me off. Economy with the ship. Government contracts. Kaput. So they had to lay off people. Of course, if you're the last one in, you're the first one out. Goodbye. And they said, when the economy gets better, we'll bring you back. Okay. This was up in Marietta, Georgia, where Lockheed is. I came back to Tampa. My sister tells me, hey, do me a favor. My friend is registering at HCC. Can you please pick her up? She doesn't have a ride. I'm like, okay, whatever. I got nothing. So I go over there. She's supposed to be someplace. I don't find her. So I start going through the hallways, right? I turn the corner, and there's a plaque, almost eye level, that says, Math Science Director. I'm like, I have a math degree, I have an engineering degree. Why can't I go in there and teach physics and calculus and algebra? I need some money. So I went in. This is Friday. School starts on Monday. I went in. I literally said to him, do you need a teacher for calc, physics, chemistry? He goes, I do. Have you ever taught? Absolutely. Never taught in my life. I lied.
You have to show a resume?
I have to show shit. He was desperate. I'll tell you what I showed him. I showed him my Georgia Tech mini degree. Georgia Tech mini degree. That's what I showed him. He goes, this is my degree. He goes, the result of the three forces is applied to the rod BC. Find me that resultant. And that resultant must lie along BC. So the resultant has to lie along, I don't know its value, but I know its direction. It has to be along here. Okay? Notice the point of concurrency. And I like to circle the point of concurrency. Wherever my red line touches, I have to show in a free body diagram. Okay? So, here's my free body diagram of this thing. Free body diagram. This is point C. I have 200 pounds from the block. I have 240 from the applied load. This angle is 30 degrees. I do have a force this way, which is the tension force. It is at, oh shit, again, his 3, 4, 5. And guess what? I have to have a resultant that is in that direction. It's got to be in the member BC. That's my free body diagram. Okay. Find me a result. Well, I'm going to do components, got 8. Magnitude, x component, y component. This is 200. That's 240. That's t. I'm going to sum this. I'm going to sum that. 200, that's 0, but that is minus 200 because it's going in the negative x direction. There's the x, there's the y. 240. That is going to be 240 cosine 30 and 240 sine of 30, which is going to give me minus 207.84 and a minus 120. Note the components. Downward and over. There's the head to tail. Downward means negative, to the left means negative. I have the two negatives. The number one thing I look for right away when I start grading, I don't even look at the numbers. I look and see, do you have the negatives? Because once you're missing, say this negative, answer is completely wrong. You didn't get the right answer. That's how important these damn negative signs are. That's my first and primary focus, is those negatives. This is going to be 0.8t negative 0.6t. How? How? Because I'm going to say this is now 4 over 5. Again, here's theta. That's theta. That's 4. That's 3. That's 5. Right? So if I want the cosine, I'm going to say 4 over 5t. If I want the sine, I'm going to say opposite 3 over 5t. Well, 4 over 5 is 0.8, and 3 over 5 is 0.6. Agreed? Sum this up. This tells me this is minus 0.8t minus 207.84. That's the x summation. The y summation is 0.6t minus 320. So my resultant is really minus 0.8t minus 207.84i plus 0.6t minus 320j. What do I know about the resultant? The resultant has to be along the negative x direction. Right? The r is in the negative x direction. So I'm going to write, hey, there is some force resultant negative I. It has no j component, must equal to minus 0.8t minus 207.84 I plus 0.6t minus 320j. Equate i's and j's. J's over here are 0, must equal to 0.6t minus 320. That says t is equal to 533.33. I's. That's going to be minus f resultant is equal to minus 0.8 times 533.33, which is t, minus 207.84. F resultant is 634.5. Pounds. This idea of making the resultant i's, j's, k's is going to be used over and over and over. And then if there's an equal sign, that means i's on the left must equal i's on the right, j's on the left must equal j's on the right, and when we get to 3D, k's on the left must equal k's on the right. That is a very common ploy to solve a problem. Okay? You with? Who's not with? Uh-huh. No. In this case, what's carrying the load from a physical perspective? What's carrying the load? Two things. One, the tension cable, and the bar. Well, the bar is only horizontal, right? Where's the load being carried? Along its axis. That's why it's along the negative. Any questions? That's all I'm going to do. Yeah, I'll do another one next week. Right-handed coordinate system. Well, what the hell is a right-handed coordinate system? Well, I'm going to show you two coordinates and they're both right-handed. Here they are right here. The one over here is the one used by Hibbler all the time. So if I look at any 3D problem, you'll see that coordinate system being used. Doesn't matter what chapter we're in. So you can see chapter 4, y, x coming out, z upwards. Y this way, x coming out, z that way. Doesn't matter what chapter you're in. That's the coordinate system he will use all the time. Look, that's chapter 5. Y this way, z that way, x coming out. Okay? So that's the coordinate system that Hibbler used. This is another right-handed coordinate system. Well, why is it right-handed? Take your right hand. Hey, place it on the first letter, X. Curl your fingers to the Y. My thumb points in the third direction, which is the Z. That is known as a right-handed coordinate system. So if you look at this one, point your hands in the first, which is out. This is basically going out at you. Curl it to the second, which is the Y. My thumb points in the Z. Okay? That's a right-handed. Is there such a thing as a left-handed coordinate? Yes. Take your left hand, place it here, curl it. There's your thumb pointing in the Z direction if it's the left-handed coordinate system. Usually on a quiz, I give you a coordinate system. True, false. This is a right-handed coordinate system. And you have to tell me whether it's true or false. Now, why am I making such a big deal of this? Well, in order to establish directional sense, we human beings, have decided there's two ways to do it. One is to express what's known as the direction angles. The direction angles, theta x, theta y, theta z, Hibbler, since he's king of statics, doesn't use that. He uses alpha, beta, and gamma. Every other textbook in the world uses theta x, theta y, theta z. Hibbler says, I'm king. I can use whatever the hell I want. And he uses alpha, beta, gamma. Now, how is alpha, beta, gamma defined? Well, from the x-axis to the force, that's alpha. From the y-axis to the force, that's beta. From the z-axis to the force, that's gamma. Okay? So in order to specify magnitude and direction, you have to specify for direction alpha, beta, gamma. All three. Yes? All three. Now, why is that important? Well, if you change the coordinate system, look, these are two different coordinates. They're right-handed. I'm going to put a force here, and I'm going to put a force there. This angle is beta. This angle is alpha. Not the damn same. This angle is, that angle is beta. This angle is gamma. This angle is, oh shit. So when you change the coordinates, even though it's right-handed, the angles go different. So you must be careful. And why do I say that? Because in the textbook, you're going to use one XY coordinate, XYZ coordinate. It's this one. On the test, I can use whatever the hell I want. As long as it's right-handed, It don't matter. Somebody got their testing manual with them? Watch. And again, why do I do this? Oh, you're trying to treat people. If I can get to it.
Yeah.
Nope. 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 Problem number 3. On an old test. Tell me what you see as far as coordinate system is concerned. Well, hell, that's not Hitler's. Is it right-handed? Start here, curl to there.
No. Yeah.
It's pointing in the Z direction. Is that right-handed? Yeah. Is it standard? No! It's not standard. Does that mean I can't do the problem? No. It doesn't. So if you're looking at this, what's this angle now? This is parallel to that. What's that angle? Beta. What's that angle? Gamma. But it's in the negative. Because positive is downward. This is upward. That's the, there's that negative side. Bite you in the ass. Because you're not paying attention to details. Notice how simple twist of the coordinate system, and it's a whole different set of alpha, beta, gamma. That's what I want to get to and tell you, please pay attention to details. When you see a 3D problem, not necessarily problems in the book, but when you see a 3D problem for me, the first thing you want to do is check the coordinate system. Is it Hitler's? Is it a standard XYZ? Is it some funky ass XYZ that Nora just put up there to fuck me over? You got to pay attention to details. Okay? If you don't, I'm going to get you. Yeah.
Why does that matter?
Why does what matter? Because we use the right-handed coordinate system in engineering. It's not that it's not valid. You got to convert it to right-handed. Because everybody's going to expect right-handed answers. How many lefties? Okay, and that's why we use the right-handed coordinate system. There's about 10 of you that are left-handed. The rest of you are right-handed. So we use the right-handed coordinate system because the majority of the population is right-handed. Sorry, you lefties. Can't help you there. Okay? All right. That said, I'm pretty much done for the day as